to use tests with Dafny, and they're both like JUnit like a test harness that you can use just with the Dafny test command. You can generate test cases, and the generation of test cases, that's done through the verifier. That is, you get semantically generated test cases. But then if you look around, you would think that, well, shouldn't there be a quick check for Dafny? Well, there isn't, to my knowledge. So maybe if you have some interest in that area, you might put that together. There's an auditor that's being used for Dafny programs. The auditor checks that the features that you use with Dafny that could be where you could be skating on thin ice, that they are highlighted. And where are those in a verified language? Well, they are at the foreign function interface. So if you want to interface with Java code, with JavaScript, with Go, Python, C#, and even Rust, and maybe KML, then you're going to write some specifications for those in the foreign function interface. And there we have found lots of errors. People write specifications that are just not correct, or they're the specifications that let them assume false, and that's bad. So the auditor checks for such things. Some development groups at AWS and elsewhere use interface description languages, and there's one called Smithy that's used a lot at AWS, and that connects with Dafny. If you look at the encryption SDK, for example, you will see that a number of things there have been generated by Smithy Dafny. Another feature that perhaps should have been there a long time ago is what I'm calling here a boogie extractor. So in the implementation of Dafny itself, there are a number of axioms that have been handwritten and these axioms axiomatize things like sets and sequences and things like that in the language. And when you have those, there could be errors. And indeed, there was one problem with the axioms for multisets that someone detected a couple of years ago. But now you can write. The part of the Dafny implementation is written in Dafny itself, and some of these axioms are formalized in Dafny with a model, and then you prove as theorems the things that become axioms, and they're extracted into Boogie. There is a standard library, and Dafny is this month. I think Dafny is 17 years old, which is staggering for me to think about, and. You would think that the language that's 17 years old would have like a huge standard library, but that's not the case. There is one that's small, and there are a number of parts in it that when you try to use them, they're really not really so great, and they don't show the best Dafny style. These have to do especially with lemmas about arithmetic, some about the collection types and things like that. And I think we need a new design. They're not following the guidelines that we ourselves promote for example, avoiding quantifiers in particular ways. There are ways that you can write things without having them around. So there's a lot more to do there. And you would think that even like an I/O library, that should be there, but there's only small pieces of that. Okay, so another good thing that has come into being in the last year, maybe a lot was added in the last year, but it's been there a little bit longer, are project files. So when you have a Dafny project, you can have a project file, and that's something that you sort of would expect. And I think that's interesting again that if you think of languages that are new, or new in the last, say, 20 years, Go, Rust, what have you, you immediately get like a build system and like a package manager and project files. And Dafny hasn't had this, which seems a little bit odd as well. But I think that comes from that the applications that you tend to go to with Dafny, a lot of them are built up from the ground up, and the people have developed their own tools for this sort of thing. And of course, we'd like to do that heavy lifting. So now I'm very happy that there are configuration files. There used to be, well, actually still is, but it's not needed anymore, the include directives. And that's that's one of these things that as a language designer, you put in because it's needed at some point, and then you realize how much it's misunderstood, and it was just a terrible idea. I should have designed configuration files long ago, but luckily other people have at least done it more recently. We've also changed the command line to be like a verb-based command line, which feels more modern if you happen to use things from the command line. Okay, so now I'm going to go into a number of slides on the language itself and how things have changed, and some new things in the language, and it really centers around, or many of the things center around types. So this font looks like it might be a little bit small for the back of the room. Is it all right? Okay, good. People with good eyesight are in the back. So essentially, so what I'm going to do is I'm going to give a brief overview of, several slides, but not going to all of the details of the types, but an overview of the types in Dafny'. So it all starts with the 5 groups of types on this slide. So there are basic types like you would expect, integers and booleans and things like that. There are bit vectors of every length. I never have liked bit vectors, but I mean they have to be in the language. But you would use the bit vectors if you do like bit twiddling operations. You wouldn't use it for like bounded integers or arithmetic, whatever. You would use integers for those. There are immutable structures like inductive data types, or what I call algebraic data types, and they exist in both inductive and co-inductive variants. Not so many languages support co-induction and co-data types, but Dafny' does. And there are tuples, which are just a special case of data types, but with a special syntax. Then there are collection types that are built in, and this is important for the language itself because you need sets to describe certain modifications. So these had to be in the language, but it's also quite convenient. I mean, a lot of specifications use these sorts of things. And so you have finite and infinite sets, and finite and infinite maps, and sequences and multisets. There are also arrow types, and if you're familiar with an interactive proof assistant, many of those are based on higher order things, and you can't even say the name of the proof assistant before you get showered with lots of lambda expressions and things like that that you have to write, and monads and stuff. That's not the case in Dafny'. I mean, Dafny' has been, looks more like an imperative language, but of course it does support all of the functional features. So, and in specifications in particular, there are a lot of, you would, essentially write them as functional programs. So there are function values, or what you might think of as lambda expressions, but they don't have to be, they could be top-level functions as well. And they're all monomorphic, even though Dafny' supports polymorphism, all of the arrow types are monomorphic. And finally, there are reference types, and reference types were in the language from the beginning, and that's essentially classes and arrays of any dimension. Okay, so these are like the basic types that you get everywhere in the language, but then there are things that you can do with these types to create other types. So, oops. And so in the last 2 years, maybe 2.5, is it longer? I don't know, 2.5 years. We have re-implemented the type inference in Dafny'. And I must say that, there are lots of things going on with a verifier, and you might think, okay, a verifier is very difficult. But for me, I think the hardest thing I have ever implemented has been the type inference. Both the previous time, like 7 years ago, and now the re-implementation. This is really hard to get right, because to get the inference, you rely on heuristics. So the new type inference relies on many fewer heuristics than the previous one did. But the type inference is difficult. So you can get the new type system by using these 3 command line flags, and several of our users at AWS are using these. So actually, this has been in use for actually well over a year, but we're going to make those the default soon. And so what I'm going to talk about on the next several slides assumes these flags. Okay, so There are subset types in the language. Other languages have different names for this, refinement types, predicate subtypes, whatever. And essentially what that means is that you can declare a type it would have some sort of base type, and then you give a constraint. And the constraint is just a Boolean expression that you give. And this has been used quite a bit in some other, some of the proof checkers. PVS makes heavy use of predicate subtypes. If you go to an interactive proof assistant like ROC, you get a lot of these as well. And so they exist in the language. The difference here is, if you compare to, let's say, F star, which also has these sorts of things, is that the types themselves are only checked by the verifier after the type checking is done. Something like F star performs the type checking as you go along, so the two are more intertwined. But in Dafny, the constraints really happen afterwards. So there are some built-in ones like nats. So the natural numbers are just a subset type. They're not defined inductively in Dafny as you would find in some proof assistants like Agda or whatever. And there are some extra arrows like partial functions and total functions. They are defined actually as subset types over the more general arrows. You cannot, a type cannot depend on mutable state. That's something that people have tried, but it's very difficult, and it's not in Dafny, and I don't see that it's ever going to be in Dafny. And subset types cannot declare members, and the reason for that is that it would be ambiguous which member you would be referring to. So whereas most types can have members when you declare them, subset types cannot. And here's an interesting thing with the type system, which makes type inference more difficult as well. And that is if you have a type, let's say, like nat, which is a subset type of integers, of course you can assign a nat to an int, as you would expect. But you can also assign an integer to a nat. So the type system is totally fine with that. And that may be shocking, but it's not so shocking when you realize, well, the difference is going to be made up for by the verifier. So if you have something that goes sort of in the wrong direction, if you will, then the verifier is going to check the constraints. But as far as the type inference and type checker are concerned, you can go in both directions. So in a verified language, when you have subset types and inference like that, you want something more than sort of principal types. In some languages, if you get some kind of, or I shouldn't say that. I should say you wouldn't be satisfied with just something that is going to satisfy the type checker, unlike in other languages. I should have said that instead of principal types. And so here's an example. Suppose that you have a quantifier, and you say for all x, p of x holds. Well, if you infer the type of this to be integer, if the type of x to be integer, that's different, then you're saying something different than if you inferred the type to be, let's say, nat. Because if it's nat, then you're only saying that p holds for just the non-negative integers. And so this matters. And in the new, Dafny used to do this differently, but now the new type inference, any inference of a bound variable like that is always going to be the base type. It's never going to be a subset type like nat. Okay, so those are subtype. Yes, Brian. Yep, thank you.
Even if P takes a nat as an argument.
If P takes nat as an argument, the type will still be inferred to be int, so that means you will get an error there. And so two things you could do is you could either declare the type as nat explicitly, or you can put an antecedent in there. Yeah. So that used to not be the case, and but it wasn't quite consistent when this happened and not with the previous type checker. So now it's consistent, but in some cases you have to write more. Yeah. So I think that's a kind of problem that that I think languages that don't look at the quantifiers like that wouldn't see in the same way. Okay. All right. So subset types have been there also for some time. I guess for about 7 years. And traits have also been in the language for some time, but they had started off very simple. So the traits can now do many more things than before. I should mention that the traits, they're like sort of Java interfaces or like a little bit like type classes in Haskell. And a difference from many other languages is that they can have data members. That's not all languages support that. So something that's new in the type system is that now it used to be that only reference types, only classes could implement traits. And that when I think, man, I mean, little world I was in when I designed that years ago. It should have been any type to begin with, and the new type system supports that. So traits can now be implemented by, well, almost any type. It cannot be implemented by a subset type, again, for the same reason that subset types cannot have members. And if you want to, so that means that you have traits that could be reference types or not. And the way, if you really need it to be a reference type, which actually is not very common, but if you do, then you just say that the trait extends object, where object is a built-in trait that says this is a reference type. And of course, all classes, they automatically extend object. So the traits has been, getting this into the language was something that we really wanted to do, and this really required rewriting the type inference engine, and that was sort of what started all of that work. Okay, so the language also supports derived types, or what Dafny calls new types. And what that means is that you can declare a type, in this case n, and you say, this is just going to be like some base type. So why would you declare that it looks like a type synonym, but it isn't? It's saying that you're going to have that the new type n is going to have the same properties as the base type, but it's a separate type. The two don't communicate unless you do some sort of explicit cast between them, and this is something that's used if you want to have bounded variables in Dafny. Then you would declare your own kind of integer and set that aside, and then the compiler analyzes some things to determine that, oh, this thing can actually fit into, let's say, 32 bits or whatever, and then it's going to compile it as such. Because the new type separates the type from the base type, that means that the compiler has the freedom to choose a different binary representation, and that's what we do with bounded integers. But people have wanted to use these for a lot of other things, and so they exist like that. And you can declare members of new types. And new types didn't always support type parameters. That's new in the last, I think, year or something like that. And what's also new is that the base type, it used to be that it could only be integer base types and real base types. But now they can be any type, or almost any type. They cannot be traits and they cannot be reference types. The reason they cannot be reference types seems that, well, if you want a different reference type, you would declare a different class. But there is one exception, actually, and that is that data types are not allowed to be a base type. That is, you cannot base a new type on a data type. And the reason for that is just that when I got to that point in the implementation, there were no requests for that at that time, so it dropped off the priority list. I would love to see that, actually. It would all fit in to doing it. It will just require more implementation. And actually, as always, one finds there are parts of the design you have to redo, but that's also a project. I mean, this is a substantial project for let's say for a student, but it would be a great one to have. A new type, you would think that the new type could extend traits, and that also makes perfect sense. That is, you declare your own type, and you say that it extends some traits. And this, too, is the thing that when I got to that point in the implementation, it turns out, well, you need to change the compilers so that they would support fat pointers in general. So fat pointer is something that tells you the type of the thing and its value. And we sort of have that in for the compiler to Java, because in Java you have like the lowercase boolean and the capital boolean, and the lowercase integer and the capital integer, and we support those sorts of. The compiler to Java understands those differences. But it turns out that that if you want to do this in general, this touches many more parts of the compilers. So again, when I got to that point, we did not have requests for doing that. So I stopped and diverted my attention to other things. But that's something I would also love to see in the language. So these two are kind of like, I mean, if you think of like matrices of I mean, what can be supported with what, I would love to plug those so that these didn't have to be exceptions. All right. Now, something that was pointed out to me sometime during the last year is that a new type can also define a constraint, just like a subset type, and sometimes that causes some confusion. And but now that the new types can be based on anything, you actually don't need that. You could think of a new type as always having the form that I have here on the slide, that you just take some existing type, which perhaps the base type is a subset type that has constraints already. That means that there's no reason for a new type to also introduce constraints. So that's something that well, whether or not we change that in language, I think that there's a mental switch there. Well, especially for me, but perhaps for others who have used the types as well, to think of them that way. All right, so part of what you can do in the language. Oh yes, please. Yes.
So Brian pointed out a question earlier about the NAT type and you have a for all x. Brian pointed out a question earlier about the NAT type. If you have a for all x, p of x, and p takes in a NAT, and x is assumed to be an int, you need to either declare the type of x or have an antecedent. Mm-hmm. So if I'm understanding this right, if we have a new type for NAT, we would not need to write any additional annotations.
Correct. Correct. Yep. Okay. Thank you. A great question. So the subset types are different because there you can assign them in either direction. So things can become ambiguous with I mean number of things. But for new types, then it's understood what it is. So if they happen to have some base type, I mean, with the constraint, then everything is understood. I mean, what you would get, and that there you can do. If the p that I had in the previous slide took a NAT, well, you can still pass in an integer. But if p took a new type, then you would not be allowed to pass in an integer. You can only pass in that new type. So it's unambiguous in that way. Yeah. Thank you.
So I was curious about this thing where you said that traits could support data members, which I feel makes them somewhat different from what traits are in Java or something like this. Because like interfaces definitely can't, right. And this seems to be fundamental to the multiple inheritance aspect. Like you need to have fat pointers already in order to support, like, what does it mean for a base type to have those members, for instance?
Right. So, indeed, I mean, if you look at like interfaces, subset types, I should have also mentioned mix-ins and traits. If you look at them in different languages, those terms are used a little bit interchangeably, and they in different languages they have different feature sets. So in Dafny you can have data members, but if you think of the data members in the trait as being a getter and a setter, then it's not so strange anymore. I mean, because then they are, I mean, essentially methods in the trait. And but then the thing that Dafny does is that if you extend a trait that has a data member, then it will give you storage for that in the type. So for example, if you have a class, it will add in storage for that, so you don't have to redeclare that and redeclare the getter and setter around that. So so in that sense, I don't think it's so odd to have them. Yep. Thank you. Great. All right. Let's see. Okay, so type checks and conversions. These have existed in the language before. However, they didn't cover. I mean, they were really spotty in what they supported, and that's much more consistent now. And I'll say something more about the type test on a later slide. But this is more consistent now than what you had before. So there are type parameters in the language. They've been there for a long time, almost from the beginning, actually. And the type parameters support things that you might think of as usual things. You can have variants like you can have covariant or invariant or non-variant parameters and so forth. there are also modes of type parameters for cardinality preservation, which in some other contexts are called like strongly positive and whatever, which actually I think is a terrible term. It has nothing to do with positivity. It has to do with cardinalities. But then there are type tests that you can then do on the. If you have something whose type is a type parameter, you could think that perhaps you could do a type test on that. Well, that's not always actually that's not allowed on the type parameters. So in Dafny', once something goes in as a type parameter, you cannot figure out or recover what that type is. Unlike in most object-oriented languages, at least, you can check at runtime what it is, but you cannot in Dafny'. So Dafny', as such, supports parametric polymorphism. So parametric polymorphism essentially means that whatever you put into that type, from that point on, you don't know what it is anymore. It's really parametric. And something I have to say about that is that, well, that's actually great for when you compile to different languages, because Java doesn't really support type parameters. It sort of pretends to a little bit, and some other languages don't have such type information at all at runtime, and we compile to them. So it's actually convenient that we have this parametric polymorphism. But if you think of it, I think that if you talk to a type theorist, they would say, of course, this is a good thing. Of course you should have parametric polymorphism. And I've been of that mindset as well. But really, when I start thinking about it, well, why? I don't actually know. Other than the compilation issue, but that doesn't seem right. So if someone in a coffee break could tell me really why do we even care about parametric polymorphism, then I'd like to hear. Okay, so a new feature for type parameters is that they can have bounds. That is, you can have bounded polymorphism. So here's a method that declares a type parameter t, and it says that it extends some trait. And the things that you can use as bounds are either traits or subset types thereof. You can have multiple bounds if you want to. Now, there are a couple of things that are not as smooth as they could be. One is that when you use these, if you use, so x in this example is declared of type t, but perhaps you would like to use x as a my trait. Well, right now you have to do an explicit cast to that to be able to, to use it as a my trait, and that doesn't seem like it really should be necessary. So that could be a perfect project for someone. I think that's much easier actually, and also the fact that you could use only traits or subset types thereof as bounds. Well, why not allow it to be any trait? You could say that it's anything based on an integer, for example. That could be nice. That's not there. That could also be nice to add. But yeah, so bounded polymorphism exists. Okay, so I talked about types in many slides, and now I'm going to talk about some other features in the language. So one problem, if you look at the Dafny' workshop last year, there was a whole session, I think 4 or 5 talks on proof stabilization. That is an issue that's called brittleness. And essentially what that means is that you have a proof that goes through wonderfully, and then you change something, or the tool chain changes somewhere, and now the proof, the automated verifier no longer finds the proof. And this can happen in any kind of verifier. If you think of a tactic-based interactive proof assistant that is going to use some heuristics to, let's say, unfold definitions. Well, maybe if it just had unfolded something one more time, it would have found the proof. And these things could change with a change in the tool change, or in the tactics, or in the program as well. But they've been more annoying to recover from in provers like Dafny'. So we've paid a lot of attention to that in the last year, and more features coming up. I'm going to mention some of them here on the slides. So one is that, and this is now related to how you organize the proofs themselves when you write the proofs sort of manually in Dafny'. If you have something that you want to assert, that is essentially you want to prove this, you want to check that a certain property holds, then before, if you wanted to prove to prove this property, maybe you had to give some other asserts, and they would typically go before this assert. And that's not a nice way to organize it. You get these long chains of asserts that look like spaghetti code. And Dafny has supported for some time assert by statements where you can put the proof sort of inside. This is also good for as a mitigation for sort of proof brittleness, in the sense that proofs become smaller or more separated. Because the proof of this property is done sort of separately and then forgotten. So whatever proof details or whatever things that you need to pull in to prove this property are, essentially like the proof of a lemma that happens elsewhere, and so that they don't confuse the verifier any further. So this was a good idea. So this idea has been extended to all statements of the language. And there's also a change, in that it used to be that assert by the proof would only be of the property itself, but not the well-formedness of that expression. So what I mean by well-formedness is, suppose that the property that you write down there divides. Well, you're not allowed to divide by 0. So somewhere you need to prove that you're not dividing by 0. And maybe you'd like to give a separate proof for that as well. And now that proof also goes into the by clause. And that's the same for all of the by clauses. If you want to organize some proofs of code to help the verifier more, you can use the new opaque code blocks. These have existed in VCC, the verified C compiler from 20 years ago, for example. And essentially, what it means is that you take a piece of code, and instead of refactoring it into a separate method somewhere else that you call, you just do it inline. But essentially, you get to write a specification for that code block. Another feature that we have is that you can hide some definitions. So Dafny tries to, whenever you have functions, it tries to unfold those functions automatically for you. And many times this is just a really great and convenient feature, and one that perhaps people coming from an interactive proof assistant, where you have to do everything manually, is surprised by. But sometimes this gets to be too much. If you have functions that are very large and they get unfolded, maybe you don't want that, it sort of confuses the verifier more and proofs take longer. Well, you can now, there was a mechanism before where you could mark a function as opaque. That mechanism is still there, and then you can reveal them. But here you can go the other way around to hide things. And especially hide star, that is hide all function definitions, is something that a number of our users are using to really speed up number of proofs. Also when you're working with proofs, ideally the IDE would take care of, would know where you're editing and would just spend all of its efforts on proving the thing where you're spending your thinking time. But that's, unfortunately, is not the case still, even after many years with the IDE. It's doing more caching and other things like that, but we still have ways to go. And so what you can do is you can mark something as only. And this is something that you would do temporarily. Let's say that you're working on a particular method or lemma. You could mark it as only, and then when the verifier runs, it's only going to check that one. And that sort of speeds things up, but it's a manual effort to put that in there. But it's something that's also being used in good ways. So these are some of the proof organization things. But all of these, I like the features that go for proof organization because they make sense in the language. They give you a way to express your proof. You're saying, here I'm going to assert this thing, but here's the proof, and you can sort of abstract over the proof. Some of these other ones are more like mitigations, and I like those less. But of course, if you want to stop mitigating or have a smaller need for mitigating, then the verifier needs to be better in various ways. And here we're putting some effort into improving the logical encoding of some things. So Dafny, being now 17 years old, the basic form of things are still as they were from the very beginning, and we've learned a lot about how you put things together to create verification conditions. So we've done some cleanup just recently. There's something called can calls, which you can think of as as a certificate that says, sort of a proof certificate that says, I am allowed to use this function definition for these parameters. That's also been not the language, it's been in the implementation for a long time, but it wasn't used exclusively. So really we got no benefit from, or not the full benefit of these can calls. And in fact, if anything, these can calls were provided as a disjunction to other things. So maybe we just really made things worse. And just as of this month, we've put the can calls are now the only thing governing the sort of these preconditions to functions. There are directives that we use to tell the verifier which parts of a proof could be used. Some of you may know these as triggers or matching patterns. And it's important to have those in there so that you can steer, that you as the tool developer can steer the verifier. And there were some places where these were not used. And one place that actually we, embarrassingly enough, have known about for a number of years and still not done anything about is in the induction hypothesis that's generated automatically. So it means that every lemma that you wrote, we produced an induction hypothesis and did not give any directives to the solver to say how this should be used. I mean, a terrible thing we should have fixed long ago, but it's been fixed. And there have been some other places like that missed triggers that we've fixed. We're going to look to see where else we're missing them right now. We're going to do some other changes coming up. There's a concept of fuel that's been very important in the verifier. And we're changing the encoding of that in a way that I think will make a big difference for how we encode or how these triggers play a bad role in various things. I think that we will get around that by this new encoding of fuel. Now, the fuel that we've used, there was one result that actually Nada Amin, who was going to give the keynote today, she contributed to Dafny a dozen years ago and implemented the fuel parameters, but also implemented a special. Actually, she implemented a special track of the fuel parameters that meant that that if you invoke a predicate with literals, let's say, or function with literals. Let's say that you want to prove something about the Fibonacci of 12, I mean specifically the literal 12, then it would, the encoding would let the verifier just unroll that function all the way to the end, which I thought was just super cool, and it's been used a lot and it's sort of on automatically all the time. But we've noticed that this costs a lot in performance. So I've had on my to-do list that we should remove this, until something that happened more recently where I've found some bugs in Z3. And I think that it could be that the problems that we saw with the performance of these were due to a bug there. I don't know. We'll have to investigate. Okay, so here's a difficult issue that is still needs addressing. And it's an issue that arises in a language like Dafny or like Java or like any other object-oriented language, but does not occur in functional languages. So people who do more, proofs of things that are all immutable things, they don't see them. And if you do Rust, Rust is really a functional language. You also don't see this issue, but Dafny has it. So let me describe what it is. If you suppose that you have a class with a field, and you have a method here that takes one of these things, C, as a parameter, and it allocates a new one. Well, you and I as programmers, we would know immediately that, of course, this C that we just allocated here is different from that D. We got the D before, and we're newly allocating the C. Of course these are different. But proving that they are different is it takes a lot of machinery. If you look at Tony Hoare's paper of his axiomatization of Pascal from must have been 1972. All good things were done in 1972, I think, right? He has a very simple way of handling this that does not work with what if the parameter here is a set of C's instead, or some other data structure that further down has some C's. Well, those are also allocated, so they will not be equal to this new C. So Greg Nelson and I had called this sort of thing in the when we did the extended static checker for Modula 3 in the mid-90s. We called it the alloc morass. And it's still the alloc morass. I mean, this is a terrible thing. And you also need it in one other place, and that is that when you update some data, you would like somehow this method needs to be allowed to allocate new stuff and update its fields. Well, what gives you that permission? Well, that's also tied into allocatedness. And because of those two things that seem rather minor, we get lots of things that we have to axiomatize about allocatedness, and it's really uncomfortable. Yep. Oh, just wait. Yep.
Isn't that just separation logic? If you have separation, like when you allocate, you get a new object.
If you have separation logic, then you don't have allocation in this way. So in separation logic, you treat the heap as essentially you have many different small heaps, and that's also what you do in Rust. Well, Rust is really a functional language. You don't have the updates in that sense, but that means that when you get something new, you have another piece of storage for it. Whereas here, it's the same old heap as before that you have. So if you have something that allows you to interchange the pointers C and D, then you can get this issue.
But this is not really a language feature; it's more of a reasoning feature, right? It's not about Rust or.
That's true, right? Yes, okay. Yes, it's a reasoning feature, and it's prevalent all over the. Dafny does not introduce, a separate logic for verifying programs. It just uses, standard techniques that have been around for, decades. And with those, you have this issue. I'll have one bullet later that I'll say one more thing about this. But yeah, thank you. Okay, so that's still an issue. My last bullet on this slide is on bugs in Z3. And I must say, in the last many years, sometimes we run into problems with instability and you look at it and you go, oh yeah, right, we're converting between bit vectors and integers. Z3 is terrible at that. And so we understand that it's not going to do it well. Or yeah, there's nonlinear arithmetic here. Okay, we understand this is not always going to work, whatever. And then we have very large examples, and there are quantifiers kicking around, and you go, okay, all right, so it didn't do all the things right. So I've given up too soon for these things. In the last several months, there have been 3 cases where I've drilled down to the Z3 level just to prune things down manually and rather painful, I would say, and found that there are bugs in Z3. The most recent one I found about a week ago actually turns out to be fixed or at least I can't reproduce it in a newer version of Z3. But the other 2, one of them was, I had a bug report that it's been fixed in a newer version, and another one is in discussion right now. But I think that some of these. So these bugs in Z3, they were incompleteness bugs, not soundness bugs. But things where you expect that Z3 would produce the proof, and you change something minor that has nothing to do with it, and now it doesn't prove it for small examples. So that certainly should not happen. So we're going to be more proactive in actually reporting these to get these things fixed, so we have a more stable basis. Okay, so there have also been a number of other new language features, and these are smaller things, but let me list a few of them. You can put attributes on things in Dafny, and that's something that is always super useful especially for third-party tools or whatever. You can say extra things, and many other languages support these with different names. And the syntax for that in Dafny has been curly brace : before. But now we have an additional syntax, and we'll see, I mean, if we keep both or just go to the new one, with an at syntax. So that looks more like the ones, like the attributes in Java, which are called something else. And an advantage of doing it this way is that now we're checking that these are really declared types in various ways. So we can do more checking on them. And that's something that the C# and .NET has done for a long time. We support parameter default values. This feature is probably more than a year old, but one that perhaps not so many people know about. So you can give default values, and these can depend on each other. That's not all languages support that. And you can call them by binding the parameters by name if you want to. Actually, what you can also do, which was a feature requested in Dafny', is you can mark a parameter as being name only. And what that means is that if you can't pass it in positionally, you have to name it. And for some people, that's been an important sort of style thing to make sure that when they go from version to version, that things are done correctly. There are decreases to and decrease and non-increases to expressions. What these are is Dafny' builds in the well-founded order that's used everywhere to prove termination. Which is a surprise to some people that you can actually have a fixed such order, but that works very well with Dafny'. Essentially, the user maps into that ordering. For most of those expressions, if you wanted to write the condition yourself that something is smaller than something else in that ordering, you had to then know what that ordering was for those types and then write it yourself. And in at least one case, you couldn't actually express it even. And now you can with the decreases to expressions. So this was added in an effort we want to be able to, when something fails, we have a little light bulb that pops up in the IDE. And if you click on that, you can say, give me the assertion, give me the condition that really fails, so that you can start working from that condition. Now that feature is still an experimental feature. It's not always working, but that needed decreases to clauses because that was the one thing that you couldn't express in Dafny' itself. There's a minor feature, which is that if you've used for all statements before, you could not use them in expressions before. You had to wrap something around it. It was painful. That's been fixed. And we're stricter about some things. If you have a method or a lemma without the body, for example, before you could do that and you would just get a complaint from the compiler later on saying that, hey, I can't compile this because there's no body for it. And now we're stricter about those things. You have to mark them as axiom if you to sort of acknowledge that you know that it's there without the body. Okay, so I have a long wish list myself of features that I would like to see in the language, and I'm going to run through them. I will not have time to go into all of the, I'm sure, very interesting details about all of these. But let me go through the list. I should say that this list, for some of these features, no one has particularly requested them. I just think they'd be really great to have. For some other ones, other people have even fleshed out some proposals for how to do it, and I would just, so here I'm just endorsing those. Okay, so first one on my list is adding, well, what to call them, both regions, linearity, uniqueness to the type system. This is something that the Linear Dafny' project had done a few years ago now. I was quite inspired by the regions there. So a region is essentially, think of it as your subheap. So if you have a subheap, you can declare, you can allocate things into it. And the intriguing thing is that if you put a subheap as one of the fields in your object, or as one of the fields in a data type, for example, it is just one field. It's not like a deep structure. Of course, inside it has a lot of structure because you have lots of things that are allocated in it. But it's just one thing, and this helps abstractions and it simplifies specifications. and which I think is a really great thing to try to achieve. Now, you can also hope for better verification performance because you've separated some of those things. You could hope for compiler optimizations. You could perhaps do some inline updates, that is, in-place updates of, let's say, sequences or data types. And here I'd like to make another comment about the linear Dafny' paper. So if you read that paper, it seems the reasoning there is to say, if you start with a program that uses mutable data structures, so classes, and you specify them the way that you would in Dafny' with dynamic frames, that can be problematic for the verifier. It can perform poorly, and you have more work to do. So then the paper seems to say, well, the solution to that is like linearity. And that's not actually what the paper does. I claim Brian is here; he can fight me. But I think this is misstated. What made a difference in the performance is going from mutable data structures to immutable data structures. But it's just that, well, if you have immutable data structures and everything is copied every time that you want to sort of update it, that gives you bad performance. No one would want that. So there, linearity kicks in, and linearity essentially is what allowed the switch from the mutable data structures to the immutable data structures. So I don't see the linearity as a solution. As a replacement for dynamic frames. It's if you have immutable things, then that's useful. Now, linearity is also useful for mutable data structures. So there are a number of things that one can do. Separation logic was mentioned. That has some sort of similar features. If you look at Viper, for example, Viper makes good use of that, the connection of Rust and these features. Now, Rust has linearity in various forms, and there are forms of OCaml that have it now as well. And of course, if it's good for those languages, then there's useful programming features, and you can do concurrency better. But you restrict the programming model. And what I think is really, amazing is that, as a programming language designer, what you try to do is put restrictions on the language so that you can avoid certain kind of errors and make things smoother in other ways. And a type system is like that. For example, we have a Boolean type and we have pointer types, and you don't mix them. And maybe that's amazing that as programmers, we don't have a reason to have a variable that sometimes holds a Boolean and sometimes holds a pointer, unless you're a Python programmer, maybe. But most of us don't, and that's amazing. What's amazing here is that you can actually have linearity, that you can write a lot of programs without having two pointers to a mutable thing. I think that's just amazing. Anyhow, so this is high on my list, but it's a big project, and and as the Dafny' team, we've had this has been near making it as a goal for several years now, but then something drops off, and it's not the most important thing for our users. So it's taken a back seat. I would actually like to see more systems programming features in general. For example, allocating manual memory allocation and other things like that. A feature that I would really like to see that I've been discussing with Peter Miller is the naming quantifiers. So I think that if you could name quantifiers, you would have a different model in how users would interact with quantifiers. Essentially, it's saying you name your quantifiers, and if you want to instantiate them or give witnesses to the quantifiers, okay, you have a name for it. Just use the other standard mechanisms for doing that. But if you don't give a name for it, well, we're going to try to give some automatic witnesses or some automatic instantiation sort of rules, which some of you may know as the triggers again. But by focusing it that way, then it really says you are in control of these things. Name your quantifiers if you want control. If you want Dafny to try to control it, well, don't, and we'll do our best. But that means that if we don't find a trigger for a particular quantifier that you write, you always have a way out. Right now we produce a warning message, and that warning message is usually ignored because the moment you introduce the quantifier, everything seems to be okay, and then later you run into trouble. So this is something I'm excited about. There are a number of things. When you put constraints, like on subset types, those constraints, in my mind, they've always been like ghost constraints. They're not there at runtime. But now, actually, we detect when we can compile them, and we compile them sometimes so you can do runtime tests and so forth. And this is odd in the language. It doesn't fit. It would be better to have these be declared as such. And furthermore, it causes a number of problems early on when you try to figure out, when you try to bootstrap the resolver and type inference and stuff like that. This would be much easier if we had declarations. But if we have a declaration, then it would be compiled by defaults, which is a switch of sort of methodology. And we have some other things with auto init that are done by default that probably we should change. There's some other like just nice language features. One that the people complain about or are surprised about is when they use the sequence and array constructors, they often have to write specifications for those like lambda expressions that you put in there. Well, there's a way around that I would like to see. And then often when you work with, especially sequences, but also arrays, you want to talk about the last element of something. Or I'd like to see a syntax where we give that, where we simplify the program text. You don't have to write so much. It's a less important feature, but one I'd really like to see. We've talked about function values in Dafny, and I think that we've gotten the semantics for those wrong, because the semantics of the function values include what a function reads from the heap. I think that should not be part of the semantic value of it, and that I think could fix a number of things. I mentioned traits, and there are a lot of things you can do with traits. One thing you cannot do is after the fact say that type supports that trait. You can do that in Rust, for example. You can do it in Go. I'd love to see that. There's something called type characteristics in Dafny, and many people have commented, well, aren't those just like traits? Yeah, sort of, so we should do that conversion at some point. Okay. Oh, yeah, and I have two more on this slide. I thought we were done. It has been suggested to have type invariance. So before I did Dafny, I worked a lot, with Peter Miller's and others on like object invariance. And there we dealt with mutable states. Things get very complicated once you really get into it. But the type invariants here that I'm talking about are things for immutable states, so they don't change. And those are much easier, and they still have several uses, and people have requested them. So that's something I see as going in. And I haven't talked much about IDE support. There are a lot of things that we could put into the IDE that's not there. But I think IDE support for writing proofs is something that would be nice. Many people request, they want to see the proof context. Well, the proof context is implicit in the data flow and in the control flow of the data of a Dafny program, up until some point where you start using functions and unrolling them and so forth. So showing that proof support, that proof context, is something that would be nice to do, and it can be done because all interactive proof assistants do that, but they don't have the automation that we have. And they typically work on an embedding of the program that you want. Sort of, it's like you're eating your food with rubber gloves or something like that. I don't know. Anyhow, so that better IDE support would be great. Okay, just one comment about the SMT solving. So SMT solving powers a lot of things that we do. And it's what gives us that automation, and I think it's a great technology. We make heavy use of the matching patterns for quantifiers. In fact, we don't use many of the decision procedures that are available. We use arithmetic, we use uninterpreted functions, and we use quantifiers. That's essentially it. People love to develop all sorts of like string theories, data types, array theory of arrays, all sorts of things people want to somehow put into decision procedures. But we're quite happy just encoding them as quantifiers. But we want those quantifiers to work. And there, it may be the case that I'm the person on the planet who has worked with triggers the longest, because I started in the 90s. Where they were implemented in the simplify theorem prover that we were developing as part of the extended static checking project. Still, I was surprised in the last year or two of a number of things that I found in the way that the things work that I should have thought about but didn't. So an SMT solver does lemma learning or clause learning. And when it does that, it pays no attention to triggers. And I can understand that because the triggers have to do with terms, whereas clause learning has to do with like formulas and clauses. So still, I had totally missed. And so I was really surprised by some proofs that went through and I really thought that they shouldn't. Which actually, that seems like a good thing if more proofs go through, but it's a problem because if you have two execution paths, let's say, and the SMT solver happens to look at one of them first, well, maybe it then finds the proof of the thing that follows. But if it looks at the other one first, it doesn't find the proof and it complains. So that's an issue of brittleness. So anyhow, I think it'd be really great for someone to rethink SMT solvers, that is, rethink the sort of the formalization of them. Many people, I can think of Shankar and a number of people have made beautiful presentations of what like all of this clause learning and how an SMT solver really works and how you do the backtracking and the non-chronological backtracking and stuff like that. But I would like to see such a simple framework, but with quantifiers added. In fact, I would like to see a minimal SMT solver. Think mini-SAT, but SMT and quantifiers. So mini SMT cube, whatever it would be called. But to just do those. I mean, forget all the other decision procedures, but give me quantifiers, because we need those. And there are other things. I mean, triggers, when you start working with them, they kind of work like just matching rules. So there's a whole big community that does rewriting. And this sort of the egg tool by Zach Tatlock, for example, and others at UW have developed that into a tool. Others have too. And there's been some proposals from Ranjit Jala and Niku Bazu and others about how you can think of like having more guards than just the syntactic triggers that we use. I think that some of those things would be interesting to rethink in this context. Okay, I think this is my last slide with some contents. So there are a number of open design questions and questions about how to do things technically and where to go with a project like Dafny'. So one design question is termination of dynamic dispatch, and for that matter also termination of applications of function values. Dafny' handles this in a particular way. The way that it handles termination for dynamic dispatch is that it doesn't allow it across module boundaries, which is, I mean, a very strict, too strict of a restriction. So there are solutions to these, but they have to fit into the language in a nice way, and we've not decided on what to do with that. And the first bullet here has been sort of open in that sense for quite some time. So that's something that needs to be done in some way. Dafny' always checks well-formedness, and what that means is, again, if you divide by something, you check that the divisor is not 0. If you call a function, you check that the precondition holds. This is something that in tools that I've developed before Dafny' was always the intention that we would do, but we never did a complete set of these things. And that means that you get a lot of strange errors, like something doesn't prove. And why doesn't it prove? Well, in the end, it turns out, well, it was because something could have been null. And I mean, in those checkers, because they didn't have the non-null types in the same way. But you're not living up to some restriction on the operators that you're using. And Dafny' checks that. And that's been, I think, a great comfort that you know that it's not that because you had something that was not well formed. But a question is, well, when you have those well-formedness checks, should they be of the should they be treated as the sort of a check and forget kind of variety, where the verifier will check it and then forget the proof of those things, that they don't sort of, well, pollute the rest of the context. And that's not how it's done for most things today in Dafny, but it may be the way to go. So the question is, what should be the scope of those? And I think that's a sort of nice, well, theoretical, methodological question. Dafny supports compilation to a number of other platforms. I mentioned earlier in the talk that the encryption SDK now is written and verified in Dafny and compiled to and released as a library for 5 different platforms now. And it's a little bit odd to have that is, the fact that we do multi-target compilation, that has nothing to do really with verification. It's just that Dafny was a good language for doing that as well, because it's a bit more abstract than those other languages, so you can compile to them. And we've gotten a number of users that have picked a particular target, and that's what they want verified code for. I think the encryption SDK is the only one that has used 5 compilers, and but there's a question there: should that really be in Dafny, or should it be in some other language? And you would think that there'd be a number of programming languages that compile to many other targets, but that's really rare. So in that sense, maybe that should be kept in Dafny, but I don't know. That's a design question, and where to put our effort. I would actually love to see a native compiler for Dafny. Dafny verifies that certain things don't happen, but then when we compile to Java or .NET, for example, or other managed languages, you still get runtime checks for all of those things. It'd be really nice to have like a best of compiler for Dafny that would just do better performance-wise. And of course, we'd like to verify the compiler. This is something that we've made small steps towards for a long time, and now there's an effort at Chalmers to use CakeML as part of that mix to try to get to verify part of the compiler. Okay, so I went through lots of laundry lists of lots of things. I think maybe the more tutorial thing that I presented was, some parts of the type system, which has become rather rich with a number of things that you can do these days. And I think that with the applications that we have, both in the academic community and in industry, of how these sorts of things are picked up, it's not like it used to be a couple of decades ago where people just didn't know verification, or would mock you when you would mention it and things like that. But it's paying off for something, including something as big as and important as the authentication engine in AWS. So I think this is a great time to be in this area. There are lots of things to do in Dafny and in similar languages. And remember, Dafny is open source. Remember to teach using Dafny and prove good things. So thank you very much. All right, I'm happy to have questions in the, what do we have, 10 minutes before the coffee break?
Can you say more about the new fuel encoding?
It's one that I mentioned to you years ago. The few is going to be a little bit more detailed. So, so the fuel is a parameter that we use to say how many times the verifier is allowed to unroll function definitions, and it's usually set to 1. That is that every occurrence of a function, so every textual occurrence of it is going to be unrolled once. And I think that's a really great idea in most cases. But we've found that sometimes we need a fuel of 2. So in checking context, like for example in a post condition, we use fuel 2. And what that means is that if you have a large function, it unrolls it and then unrolls it again. So essentially you get a quadratic blowup. And most of the time that's really not needed, and we get lots of extra clutter. So this is a problem that we want to solve. So the way that the fuel is encoded today is that the fuel parameter is added as an extra parameter to the functions themselves. I'm talking about, this is under the hood in Dafny now, right? So you would pass in the fuel parameter. So if you have the Fibonacci function, it takes not just the Fibonacci argument that you want to compute the Fibonacci function for, but also a fuel parameter. Well, this is causing a lot of problems because then when we write other triggers, you have to be careful in matching that up, that fuel parameter up with other things. And so we've actually put in quite a complicated machinery in Dafny that would allow you to specify the fuel in various places. And this is also what causes us why we needed a fuel parameter to be 2 in checking context. So the better way to do it is to make use of the can calls that are now in place. So a can call is like a certificate, again, under the hood, that says we've checked that these parameters in this context are good ones that you can use for instantiating the function. So you would be allowed to unroll it. And it would just make sense to, in that certificate, to also say, hey, by the way, you're allowed to unroll this 6 times or 1 time, or and most of the time it would be just once. So that means that these fuel parameters, of course, for fuel to work, they have to be part of triggers. But that means that the fuel will be part of triggers only for definition axioms and consequence axioms, not anywhere else. And that, I think, is going to clean up the encoding, and especially since we can avoid that fuel too, I think is really going to help. So, yeah. Yep.
Thank you. Could you say more about the boogie extraction feature?
Yeah.
Like what is extracted and under what conditions?
Right. So let's say, suppose that you have something that like sequences or multisets. Let's say sequences, and now you want to encode some axioms for that, so that the SMT solver, you want to tell the SMT solver what it can do about these things. Well, then you need to have some axioms that you would give it. So these had been written by hand before. Now, if you talk to someone doing interactive proof, like using an interactive proof assistant, they would immediately think, oh, well, we're not going to have these axioms, of course. We're going to write some sort of model for these things and then prove theorems about that model. And then those theorems that you have proved, those could be used as part of the proofs. So what we wanted to do was to give a model for sequences and some other things, and then prove theorems about those models to say these things really hold. But then once we have those theorems, we want to give them to the SMT solver. And that's what the boogie extraction does. So it extracts those theorems that we have proved into the form that essentially that we can pass, that's part of the Dafny verifier itself. So of course, Dafny all the time takes any kind of program and translates it into boogie. So one might say, well, why is it different? Well, in the normal encoding of things from Dafny into boogie, it adds a lot of things like the allocatedness and the types and all sorts of things. And you don't want them there since this is part of the implementation. So therefore, the extraction feature is a cleaner, leaner kind of thing. It's specialized for this sort of thing. And one final point about that is, again, if you talk to someone using an interactive proof assistant, they would immediately think, oh, we should do this in some other tool. Well, of course you shouldn't. Dafny is a verifier. You should do it in Dafny. So these are done in Dafny. Yeah, thank you.
So if there are no more questions, then I will ask one question by myself. So I was wondering about the proof brittleness and about like the restructuring of the proof. Mm-hmm. And my question is like, how does restructuring or like the organization solves the brittleness in the sense that how do I know how many times I need to unfold, or do I need to do some more things?
Yeah, right. So a number of questions there. So one large thing that we have noticed where brittleness comes in is that when you have if you have, in general, larger proofs, then there's a larger chance of brittleness. We can measure, we get a resource count, which is a measure of how hard the verifier had to work. And we have found correlations between if those resource counts are high, then we have a lot of variation and that tends to go with larger proofs. So then one thing that you would like to do is you'd like to make the proofs smaller. I mean, the way I'd like to think of it is that you'd like to give fewer things to the SMT solver so that it would get confused less often. I mean, otherwise it would say, ooh, squirrel over here. I'm going to like instantiate all of these things and unfold functions and do case splits and stuff like that. If you give it less things to look at, then you would be better off. So the features that let you compartmentalize the proofs, I think, are good structuring things. And I think, I mean, as programmers, I mean, we like to have extra methods. We refactor our programs. We don't like write long monolithic programs, and the same should hold for proofs. So those features are good both for organizing your proof and for reducing brittleness. So then your question was, well, how should you know, like, how many times you should, well, unroll things? And some people, they learn about, I mean, triggers, and then all of a sudden they think that they have to write all sorts of triggers, and they do, and they all, I mean, they make mistakes, and things don't work, and it's awful. So I think that all of those things should really be out of the way of the user. The user should not have to think about this. So instead, I would encourage you, when you have a proof and it doesn't go through, then you ask yourself, well, why doesn't it go through? Well, does it know this thing? Does it know this thing? Or you start writing the proof by yourself. And what we would like to do is that once you've written such, I mean, if you have to write the proofs like that by yourself, that it should be stable. But that's that's our responsibility to stabilize the proofs. But you may have to write manual proof steps. But when you do that, the question that you always have is not like, how many times should I unfold this, or how should I tweak the parameters? You write the proof. That's and you don't have to think about that in coding. So that would be my or at least that's my design philosophy in I mean, both for the language and for the verifier and the IDE, whatever. We should try to remove these from sight from the user, because users, I mean, don't do good things with tuning the parameters of things. Yeah.
All right, perfect timing. Let's thank Rustan again.
Right. Thank you very much.